All right, well, it's my great pleasure to introduce Kris Dorsey, who's my colleague and friend and an amazing roboticist. And Professor Dorsey is an associate professor in the ECE department at Northeastern with a joint appointment with the physical therapy, movement, and rehabilitation sciences. And she's a core faculty member of the Institute for Experiential Robotics at Northeastern, which is a really cool institute that focuses on integrating human interaction and the human experience with robotics and really focusing on making systems that interact well with people and in different ways. And Professor Dorsey is an alumni of CMU and Olin and has won a number of awards, including the NSF Career Award, the MLK Fellow at MIT, and also the Emerging Leader Award from the Anita Borg Institute. And I think it's pretty cool that we just a couple weeks ago had Rebecca here giving us a soft robotics talk, which was mainly about the actuators and applying to bio-inspired robots. And so today's talk, we actually get to see the other side of soft robotics as well, which is the sensing side, and also applications that can look really different from the kinds that they did. So this is an exciting semester for me because I really love Kris's work. All right.
Thank you. Thanks so much for that warm introduction. All right, so to Radhika's point about the Institute for Experiential Robotics, I meant to include a couple of slides about what we do and what our facilities look like. I did not, and so if any of you are in Boston, I would love to give you a tour. We just opened a new building that includes all of robotics on the first floor. So if you're in Boston, please come see us. So today I'm really excited to talk about my work in designing sensors for soft systems. So I'll talk about wearable devices, typically embedding sensors in fabrics and garments, as well as soft robots. And I know the seminar series spans a wide number of topics in robotics, and so I want to start out by talking about some of the reasons that we might want to build a soft robot rather than a lot of the traditional rigid robots. So definitely we might want to consider the material advantages of the soft robot. So an idea that has been floating around in soft robotics for quite a while that soft roboticists are now starting to grapple with a bit, but I think still is one of the strong advantages of soft robotics, is that by using these soft materials, by using fabric, paper, silicone rubber, other materials like that, we can make these robots safer for people to interact with than robots made out of rigid plastic or metal. And that makes it a lot more advantageous for doing things like interaction, where we want someone to work with a robot in a conformal way, maybe placing a garment or a sleeve on someone's hand, as well as assistance and definitely healthcare, which is a major focus of my talk today. Another big advantage of soft robots that we get out of the material and this more continuum movement is that we can use it for things like bioinspiration. We can look at some of the interesting properties that we get from bistability by flexing and deforming these materials, and softer grasping and interaction than we might be able to achieve with a rigid gripper. And so one of the things that underlies both of these challenges is that in order to do a lot of the things I just showed you, we need a sense of proprioception and exteroception. That is where the robot understands itself to be, where are the different parts of me, what's my pose, as well as exteroception. So what am I touching, what's going on around me? With wearable devices, maybe what the wearer is doing. And these are major challenges in soft robotics that lots of researchers are interested in working on. So today, I'll talk about some of my lab's approaches towards the sensing component of proprioception and exteroception. Of course, there are many pieces in addition to this beyond the sensors, but I am really excited to share at a fundamental level how we get information about the robot's pose or the environment around it for additional signal processing and eventually perception. So a lot of the traditional approaches that we use in robotics, vision, encoders, those sorts of things, for this fundamental sensing level of these challenges don't work quite as well when you're talking about a soft robot. And so my plan for today is to talk about some of these challenges at the sensing level towards proprioception and exteroception. I'll talk about one major bin of applications in wearable device design and some of its applications to a health challenge. And then finally, I'll wrap up with some actual soft robots and talk about my lab's work in soft origami robots based on a module called the Kresling. It's over there on the left. All right. So one of the challenges that we have with soft robots is that we are asking them to do these very continuum motions. They're stretching. These motions happen in materials that are typically also highly nonlinear, highly viscoelastic. And so that adds all sorts of additional very fun challenges, or at least challenges that keep us all in business as researchers, into understanding what these robots are doing. So in the context of where we want to deploy these sensors and where we want to deploy these robots, we have challenges where the robots, we typically want them to be untethered. So that makes structured environments where we can place cameras and understand how the robots are moving in a scene more challenging. We may have someone self-obscure by moving one limb in front of the other. We're working on a study in my lab right now in asking people to move around in a warehouse-like space as they pick up and put down boxes. And one of our most vexing things for motion capture is when people stand like this. It's a very normal pose, and we have had to very carefully place where we put the motion capture and ask people, please don't do that, because we want to get really clean data for this paper. Thank you. All right. So usually another challenge here is that when we talk about soft robots and the applications that they're really good for, is that they are applications where we're taking advantage of the materials, we're taking advantage of the ability to fabricate them quickly. We may be pretending or working in areas where we don't need as much precision as we would from a 6 degree of freedom arm. And so that usually translates to something that's cheaper. If I were to take a bunch of robots and throw them out in a field and have them go do environmental surveillance, and only 90 of them come back, that's much more acceptable if each of those robots is $100 than $100,000, obviously. So our sensing approaches also have to be less expensive. They also have to handle lots of environmental conditions, anything from the field robotics that I just mentioned to lots more deformation in whatever their application is. In addition to the challenges that I just mentioned about the wearability of the sensors is also the challenges of the flexibility. So with these flexible materials, because we are asking through our actuation approaches for these robots to deform, to stretch, to twist, we also need sensors that can do those motions along with them. I'll talk about this a little bit more towards the end of my talk, but one of the major challenges then is delamination. If you have a rigid material or an inflexible material, that it just comes apart from your actuator. And so that's another one that we'll need to solve as sensor engineers. So those are two reasons that we want other sensing approaches aside, at least, from vision and encoders. And so for the rest of my talk, I will talk about mechanical solutions to this idea of proprioception. And I just want to give a little bit of a shout out. I'm being a little cheeky or a little coy here. One of the most successful applications, commercially of course, of this sort of soft deformation is tactile sensors like the gel site, which have this really cool fusion of soft materials and vision and rigid components. For the purposes of my talk, I'm going to gloss and say that we're going to focus on really soft material sensors, but of course, depending on your application, depending on what you want and need the robot to do, the performance, approaches like this may be way more appropriate than what I'm going to talk about for the rest of the day. All right, so there are a couple of different approaches that soft roboticists take to get these new sensors. One is using soft, stretchable, and flexible materials, novel and new materials. So I will refer to this as the material science camp. I am not a material scientist, and so I think this approach to new engineered materials is really cool, but largely we're going to be using unsophisticated materials, just silicone rubbers, conductive fabrics, rather than the newest, coolest hydrogel. The other thing that we need our sensors to do is to withstand millions of cycles. So one of the major applications that get talked about for soft sensors is being able to understand where someone is distributing the weight on their foot, or for things like understanding heel strike force. Let's embed a sensor in the heel of their boot and measure the ground reaction force. If we do that, let's say we want their shoe to last for 7,500 steps a day, and we need it to last for a year. That's already nearly 3 million cycles, and is well beyond what most researchers do to understand the degradation in performance of their sensors. So these sensors need to be robust to delamination and wear, withstand extreme cycling. And then one of the challenges that I'll really focus on today in this talk is in distinguishing different kinds of mechanical inputs or being highly selective to one type of mechanical input to another. So I'm going to show a video and ask for a little bit of audience participation here. And, oh, that was a perfect time for that to go out. Thank you. All right. Let me try that one more time. Apologies. So this is a sensor that I have fabricated in my lab. It is a silicone rubber body with a spiral capacitor made out of liquid metal, highly stretchable. And my question to you is, during the video, what did you notice? When I press it, the capacitance goes down. Cool. Anybody notice anything else? So, yes, great eyes all. So there is a small decrease in capacitance before I actually physically touch the capacitor and then squish it. Anybody know why? What? You got it, yep, yes. So I am changing, because I am a conductive person, I'm distorting the electric field around the capacitor. It changes the capacitance. This is only one example of lots of different types of sensitivity that our sensors may have, to temperature, to torsion over bending. Typically with these sensors, we want them to be able to sense just one and one thing: strain but not pressure, pressure but not torsion, pressure but not proximity. And so this is a major challenge in sensor design, and one of the reasons that I think paying attention to sensor design when we talk about how we get better proprioception in soft robotics. All right, last challenge that I want to talk about is sort of linked behavior of drift and hysteresis. So ideally, our sensors, in the paradigms that we like to play with them right now, highly linear behavior, highly repeatable behavior, this sort of behavior, this hysteresis where we get different force extension curves or different output curves with loading, signal output curves with loading, is really not ideal. If we have, for example, let's go back to the ground reaction force example. If when I load and then I unload, on my sensor in my shoe, I get 2 totally different responses. That makes understanding what I'm actually doing much, much more difficult. And so engineering and figuring out how we reduce hysteresis in these cases is another major challenge in these soft sensors. Okay, so the key theme that I want to emphasize throughout the rest of my talk is that through better sensor design itself, at the very fundamental level, what does our sensor look like? What materials are we using? How is it structured? What's the modality? All of those leading to better sensor design can offload a lot of the processing that we need to do afterwards, which is advantageous for some of the initial things that I talked about with wearable and soft robots, related to what the cost is, related to what resources we need if we can operate this with a microcontroller or we need a GPU sitting next to it. And so this is, by and large, the focus of my lab's work. By the way, I understand Hadass was here a couple of weeks ago, and there's like a nice interactive back and forth. So if y'all have questions at any point, I'd love to take questions in a moment. Yes, please.
So if you are willing to pay the computational cost, does improving the design also lead to better ultimate accuracy, after all possible processing?
Yeah, I would think so. Even if the computation is not a consideration, improving the sensor itself will lead to other better outcomes. So one of the things that I'm thinking about is there are a lot of applications with soft robotics where you don't care about how much training data you need because you're going to put it in the same vehicle afterwards. But for wearable devices where my morphology is totally different than everyone else's in this room, the way I behave, all of that would require some sort of customization per person. I don't know if you've ever, like back in the day, had to train some of the natural language processing or those other training things. It's a fairly frustrating process. And so I think there are other benefits just besides reducing computation to having better sensors. Yes. Yeah. Okay. Yeah, I like that as well. And I think it's always a really interesting question about, like, at some point there's going to be diminishing returns about you're adding more sensors, but what additional information is that giving you? But yeah, I think right now we're largely in soft robotics at the stage of like 1, 2, 5, 10 sensor, 10. Wow, on a robot. So yeah, absolutely. I think that's a great point. Thanks. Yeah, I can. I was thinking when I was putting this talk together, I was like, I think I want to just leave IMU out and see if I can dodge the question. No. It's a fantastic question. I'm glad we can talk about it because I think particularly for wearable application where you're just trying to extract, let's say, joint mechanics, joint kinematics, that IMUs do a much better job than soft and stretchable sensors at this point. The performance is better. We know how to extract and play with the data much better. Like, you should just use an IMU. And so where soft sensors really shine, I think, is in when you need stretch and when you need pressure. So there are also like very cool approaches coming out where you use a MEMS pressure sensor with a soft membrane over it. That also works really well. And so, yeah, I do want to emphasize that I don't think this is like soft sensing is it or nothing. But I think the performance does need to come up to get to the level that a lot of these other sensors are already at, thanks to MEMS over the last 20 years, and we're not quite there yet. Yeah. Oh, please. I'm thrilled.
No, but very quick, I want to get back to things. This is very exciting. But since we're talking about the role of IMUs, one of the, someone who's done work with drones and mobile robots, one of the really horrible things about IMUs is they drift, right? Because they're just measuring acceleration and they're giving you rate measurements, but then if you're just relying on the IMU, your status limits are going to be, you put some IMUs in someone's, jumper or sweater, and then suddenly their arm is just like floating away in space. So it seems like there's maybe a very nice sort of complementarity between that and the kind of soft sensors that can give you sort of absolute measurements of either position or relative angle and so on. So it could be that the sensor fusion between the IMU and the soft sensors is actually what ultimately seals the deal.
Yeah, I totally agree with that. And just for some fun background here, my dissertation work was firmly in microelectromechanical systems, trying to make better accelerometers that didn't drift as much. So yeah, I can absolutely agree with that. And it's like, yeah. All right, so I want to tell you about one bucket of work related to wearable sensor design for applications to health. I'll talk about the health application first, and then I'll get into the wearable sensing bit. So you may or may not be familiar with a health condition called edema, fluid retention. This is related to lots of chronic venous conditions, so chronic venous insufficiency, lymphedema. It's also observed in things like end-stage renal disease when someone has trouble regulating the fluid, the volume in their body. And so this condition is illustrated nicely in the photo on the bottom left. That's an arm of a woman who developed lymphedema after breast cancer treatment, surgery and radiation. And the photo on the top is her arm before she had surgery. The photo on the bottom is after she had surgery to remove some of the impacted tissue. And so one of the challenges with this disease is if the fluid continues to accumulate over time, particularly in lymphedema, it actually causes structural changes in the tissue. So the tissue itself becomes more fibrotic or woody or spongy. This creates challenges with limb mobility. It's a major impact to self-image and self-efficacy. And it also has like a lot of other negative outcomes that I don't want to delve into to take it too negative, but just to drive the point home, major health challenge that is not currently addressed well by digital health tools. So most people, if they develop an edema-related condition, particularly lymphedema, the clinical surveillance piece looks like they at some point report, oh, I'm having one of the symptoms that you warned me about. My limb feels heavier than my other limb, or I'm noticing my jewelry is tighter, or like it looks weird. And then they'll go into a clinic and they will get tape measurements. They will be measured every 4 centimeters, and then the volume of the limb will be estimated. And then the clinician over time will track the volume of the limb. At some point, if the volume gets too large, then it's considered increasing to the next stage of edema. If an individual lives near one of a few select hospitals in the country, such as Mass General, they have this optical tool. It's really cool, called a pyrometer, where the box in the middle slides over the arm to optically map the volume of the arm. But in both of these cases, someone has to come into their doctor's office or their physical therapist's office, get these measurements. If they live far away or they have trouble getting to the doctor's office, measurements are just by and large not available to them it's reliant on their surveillance only. One of the things I'm really interested in is developing new tools that can answer questions about this constellation of health concerns, such as like how limb volume is changing over time, are particular lifestyle changes or pharmaceuticals or decompression techniques more effective for each individual? Is the compression garment applying the right pressure? And then I'll talk about the robot in a second, but I really want to emphasize this second question here, which is once someone develops lymphedema, chronic venous insufficiency, it is a lifelong condition. They need to wear compression garments nearly around the clock for almost all of their lives. And these compression garments are relatively expensive. You need to go get fitted for them about annually. And in speaking with clinicians, one of the challenges that they identified was that individuals don't want to come back to the office and get a new compression garment because, no, thank you. The old one is fitting fine. I don't know if any of you have had the same favorite pair of sweatpants or any other elastic garment for many, many years, but it does not necessarily hold the same shape that it does now that it did 5 years ago. And we are not, as a research community, as a clinical community, measuring what the garment is actually applying to the individual over time, which means that these garments may not be as effective as we need them to be. So that's the sensing side. The actuation side is, so typically over the last 20 years, people have developed these intermittent pneumatic compression pumps. They are big sleeves or socks that go over the limb and sequentially squeeze. They do look quite a bit like a big soft robot. These pumps are not portable, typically. They are very bulky, certainly can't be worn under clothing. So in the last couple of years, there's a new product that has come out, very exciting, called the Dayspring from Koya Medical. And so this individual is wearing the Dayspring. I don't have any connection to Koya, by the way. But so this individual is wearing the Dayspring. It's much smaller form factor. The control and actuation unit is portable. As you can see, he's got it over his shoulder. But this is still something that maybe someone wears around the house. Maybe they wear it in their yard. They're probably not going to work with it. They're definitely not taking the subway with it. And so I think we have a long way to go with soft robotic approaches and actuation to making these sorts of devices much more portable and wearable throughout the day. All right. So I want to talk about a couple of pieces of strain and pressure sensing that I've been working on over the last couple of years to lead, hopefully, to these applications in the next couple of years. So this is a collaboration that I was working on with Rob Wood's group a couple of years ago in trying to map gestures made at the hand trying to map changes in muscle tone to gestures made at the hand. So fantastic. I see a couple of you in the audience already doing it. But if you're wearing short sleeves or can roll your sleeves up, you can see making different hand gestures changes the muscle tone in your forearm. And we placed sensors in a sleeve in order to distinguish those hand gestures. In this case, just 3: open hand, closed fist, fingers pinched together. So this is going to show wearing the sleeve with the 3 sensors on the forearm, 1 just above the elbow, making the 3 different hand gestures, and then the ground truth, motion capture just for ground truth. Also tracking wrist angle. And I'll speed up here for just a second. Also, last demonstration of click versus double click. So the original vision for this sleeve was for human-robot interaction in areas where it would be pretty challenging to have to have cameras because of occlusion. Certainly voice commands wouldn't work in a really loud place. And so the idea being that you could like gesturally communicate without encumbering your hand with a robot by doing something like saying, come forward, come forward, come forward, stop. And then interpret those gestures through the sleeve. I was quite excited about the potential for using these strain sensors to not only map to particular gestures, but for the much longer term challenge of volume estimation. So we've already got a compression garment. We've already got strain sensors embedded in that compression garment. Can we then use that to estimate volume? So my role on the project was in modeling the sensor performance. I'll tell you a little bit more about the sensor. So we start out with a sheet of laser micro-machined carbon fiber. Carbon fiber works really well for this application. It's nicely water resistant. We machine it so that it is elastic, and then we can lay it up with other materials. So we take that micro-machined carbon fiber sheet, we adhere it to a piece of pre-stretched elastic material, and then when we let that stretch go, that causes the gaps within the serpentine to contact each other. So what we end up with at no applied strain is a structure where we have one conductive path through the serpentine, the material itself, but also paths in between serpentine. It can take a shortcut from one to the next. And then when we apply strain, that takes away those contacts, and we increase in resistance. By the way, when we were first modeling this, we were thinking about trying to understand where in the sensor the elastic behavior starts, and we actually got. We were talking about how it's like a slinky. If you have it squished up, low resistance. If you expand at high resistance. Jaime, I saw your slinky today. And we actually did a short experiment with a high-speed camera and a slinky to show where it first starts moving to answer an in-group fight. All right. So as I mentioned, my role was in modeling. There's an electrical component to the model and a mechanical component. The electrical model uses good old bog standard nodal analysis with changes in the contact resistance to map the resistance at different forces, and then a strain energy balance to understand which contacts are in contact versus not. So this plot is showing, as we tune different sensing parameters, as we change the length and the width of the carbon fiber serpentine itself, how does that change the strain sensitive response? The dark line is showing the average performance of the sensor. The dark line is showing the model. The shaded area is showing the range of all sensors that we measured. So what I like about the sensing performance is we get a sensor that is very sensitive in short range of strain, 2 to out to 4 or 5% strain. So there's a bit of a gap in soft sensing where you can get micro strain from things like flexible strain gauges, and then you can get very large hyperelastic strain from something made out of silicone material. But something that is sensitive in this range to 0 to 5% strain, those sensing demonstrations are more limited. So being able to distinguish minute changes in arm muscle tone is right in that range. The other thing that I was really excited about with this sensor towards future applications related to edema monitoring was that it is sensitive to strain, but it is not. It does not have large cross sensitivity to curvature, to torsion, or to bending. So those are the three shown on the right, which means that if we could likely distinguish changes in strain, but if somebody is crossing their arms and now applying more pressure, resting their forearms on their desk, anything like that, that we won't respond to those deformations as well. All right. So with that lead up, I want to change gears a little bit and talk about the edema monitoring piece rather than the sensor device piece. So this is work that my student Damla completed last year and presented at the IEEE Sensors Conference related to just, can we measure changes in arm volume quickly over a short time period using some of these strain sensing approaches. So our approach here was to design a study where we induce swelling in healthy participants via arm exercises. So if any of you are weightlifting or gym people, colloquially, they were getting swole. We were then measuring the change in upper arm circumference with both a sensor and a clinical approach using cloth tape in order to discover whether a gesture set that the participant was doing would mitigate non-idealities, so the sensor moving, changes in participant sweating, any of that, across time. So for that third component, we're still doing data analysis and collecting additional data, but I'm excited to tell you a bit more about the initial participant study. So we had a sensing sleeve with two sensors on it, two strain sensors, one over the bicep, one over the tricep. And these are very straightforward capacitive sensors, multi-layer, but as they experience strain, the capacitance increases because the sensor is stretching and the electrode to electrode gap is decreasing. So we're measuring the capacitance of those two sensors with a small custom wireless board in the middle there, and then just tracking that change in capacitance across the study. So despite the fact that there's nothing particularly, oh yeah, question. The sensors are not overlapping. Oh, so the sensors themselves are the silvery material, and we just have two nylon fabric tabs to hold them in place on the sensor so that they're fixed relative to the rest of the sleeve. Yeah. All right. So despite the fact that we're not doing anything super fancy here with our sensing approach, we do have nice performance out of our sensor, response time or a settling time of less than 200 milliseconds, 5% drift error, and hysteresis, or a speed dependence of 7.3%. So this sensor, in and of itself, is good enough for our study where we're trying to map these changes, but certainly if we wanted to measure more minute changes in terms of edema, that's something that we would want to improve for these. So our 3 participants came in, performed arm exercises to increase the volume of their upper arm, and then performed these gesture sets. And what's being shown in the bottom left is the sensor output of the biceps, the output of the bicep sensor during the arm motions. So we're still uncovering whether the gesture set itself can help us decouple some of these non-idealities. We also do need to collect data with additional participants. But for this initial study, we were really excited to see a mapping in baseline capacitance that mirrors what we would expect physiologically and what we observe in terms of arm circumferences. So the pink line shows the output during the gesture set before, directly after exercise when we would expect fluid to be most accumulated in the limb. We see the largest baseline shift that then decays over 10 and then 20 minutes. That does track nicely with the change that we see across participants in arm circumference at different locations, directly above the elbow joint, directly below the shoulder joint, and at the widest part of the bicep, or equidistant between those 2 points. All right. So I want to wrap up the sensor bit and say that I think this approach with different sensing modalities is really exciting. And even with these simple capacitors, we're getting some signal that the approach towards lymphedema monitoring is possible. But there are a ton of questions that I'm really excited about getting a sensor platform in place to answer with clinical collaborators that include what are the person-to-person variations. If I take a sensor that is made for me and then I give it to a friend, I give it to someone else in my lab, how does it perform on them? How does the estimate change? Also, if I take that sensor off and I put it back on, obviously the position will be a little bit different. How do I compensate for those changes? And then finally, the data, and the sensor is only a small part of this larger challenge of edema monitoring related to data, privacy, and being able to take action related on what the data are telling us. Yeah, Amy.
It's really cool. One of the things that I was thinking about as we were talking, like with the hand gestures or even the movement is there any benefit, so as you design the electrode and it's going on the substrate, is there any benefit of shaping the substrate maybe tailor the thickness of the substrate or to tailor the sensitivity or to, for example, allow for the sensor to be able to pick up, if they the overall stiffness, you're able to pick up, let's say, parts of the muscle more than others, things like that, or there's no really benefit in that, it's better to just shape the electrode itself?
Yeah, that's a great question. So you're talking about the thickness of the dielectric layer, or that one? Yes. Yes. Great question. I want to go back. I didn't talk about this, but I don't have that slide. Darn. Okay. Yes. So this is something that I did a little bit of additional modeling on that I have not gotten back to since this work, but in tailoring the shape of the underlying pre-stretched membrane does change your sensing performance. And so one of the things that I was working on was like, can we tune so that it's really sensitive in this range and then less sensitive in this other range? Yes, absolutely. That is something I want to get back to. Yeah. Other questions? All right. So it is Friday now, almost afternoon. A big part of my talk was talking about soft robots. Where are the soft robots? They're here, finally. So I am excited to talk about some work that my lab has also been doing in soft origami robots. I want to talk first about why origami, about other things. One, very visually cool, but two, because I think origami fuses the nice domains between completely continuum motion and rigid linkages in a way that we get prescribed motion of the folds, but still by combining multiple of these modules, such as Renee Zhao's work up at the top, we can get these things that behave like continuum systems. So primarily I will be talking about this particular module called the Kresling module. So it is a set of two hexagons that are rotated relative to each other and then folds in between, such that when it's compressed, it both twists and compresses in 1 degree of freedom with 2 link domains. So I'll be talking about what my lab is doing to sensorize these Kresling units towards that sense of proprioception. So what we're doing to turn this from origami into a robot is that we seal these Kresling units, we apply a vacuum, and that causes the unit to compress and twist. And when that compression and twisting happens, we're measuring the fold angle between any two neighboring folds, again using capacitance, by the fold decreasing in angle, the capacitance, the the gap between the plates decreases and the capacitance increases. Just to show you what that looks like on a Stewart platform-like origami robot. There we go. All right. So as I mentioned, the position of the top face relative to the bottom face is linked by both the rotation of that face as well as the contraction. There have been a couple of amazing groups that have described kinematic models for this. And one of our first questions was, great, all of these models are in paper. Paper works really well with origami because we want to fluidically actuate this akin to other soft robotics approaches. Does this still work if we're using something like thermal polyurethane instead of paper? So we investigated the rotation contraction relationship, and that does fit the model really nicely. So even though we're using this elastic material rather than paper, which has some different mechanical properties for holding the angle, the stretch of the faces, all of that, we can still model it well with these existing approaches. As a little bit of an aside, one of the things that we don't see with this behavior is the bistable relationship that you do observe in the Kressling unit in paper. So in paper, it has a stable state when it is fully extended. It also has a second stable state when you contract it. It will actually hold at the lower state. Because TPU has that strain energy stored in it, it does not hold that other stable state. So this is what the force displacement curve for TPU looks like. It's you can see that it's approaching bistability at about 15 millimeters of displacement, but doesn't quite get there. It pushes out of it, which is really fun and interesting for both a sensing and future control piece. But an interesting divergence from the paper-based performance. So to fabricate these, we start out by 3D printing the TPU. We print the body and then print a lid, seal it, and adhere the electrodes just by cutting out the electrode shape in a conductive nylon and adhering it to the body of the robot. I imagine at this point, some of you might have questions about why it is shaped, the electrode is shaped like that. I'll get to that in just a second. So we are using these really oddly shaped electrodes. And one of the questions that we had at the beginning was, we've got this very non-standard capacitor that we're trying to estimate the fold angle. Should we just have triangular shaped electrodes, or should we have a different shape? And so, for example, my corner's way out at the sides, maybe that's wasted area because the capacitance far out from the fold is not going to contribute much versus the material close to the fold. So to answer that question, we did some optimization using an evolutionary approach where we started out with 5 initial sensor designs that we thought kind of nicely span the space of what our electrode might look like, and compared and optimized each of them by moving the points of our initial shapes until we got to the best performing optimized electrode, which is the one in the bottom right. So we don't see a ton of change across all of our optimized electrodes. What we drew away from this primarily is that what matters the most is having material towards the center rather than having a particular shape. Particularly when we try to take this knowledge and apply it in the real world, where we do have slight variations in where we're putting the sensor on the robot. And so then we compared our optimized sensor to a triangular a full triangle sensor. And we were getting less sensitivity to less change in capacitance as displacement with the optimized sensor than the triangle sensor. However, I mentioned earlier in the talk about delamination, and realized that part of the problem was that we were delaminating these triangular sensors, and that this triangular sensor would not work for the reasons of being able to measure consistent capacitance across time. So we stuck with the optimized sensor. I apologize, I realize we're very close to time. So I will show you a couple of results of using the sensors for proprioception, using PID control to hit particular set points, to change set points, and to do trajectory tracking. So in this case, tracking a sine wave. We then applied this to two-dimension Kresling, so one stacked on top of another with anti-rotations, such that we can either rotate and translate, rotate the opposite direction and translate, or purely translate. There we go, on the purely translate. All right, so one of the things we're working on lab now is expanding these out into larger multi-degree of freedom systems. So this is just open loop, non-sensorized, but in building systems of these Kreslings and then sensorizing. All right, so with that, I think that the challenges that underlie the design of soft sensors for both wearable and soft robotics systems have a lot in common. Again, like as we were talking about earlier, I think a lot of the performance is not the same yet as vision or IMU. And I'm really excited that there are different approaches that we can apply to soft robots and figure out where each of these sensing approaches best works for the challenge of proprioception. So I want to thank the support of the NSF Career Award, all of my fabulous students that have worked on this work with me, and a couple of collaborators. And with that, I will thank you for your time.
Before we can stick around for 5 minutes.
Yeah, please, yeah.
I'm not sure if there's a mic.
Oh, there is a second mic here, yes.
Perfect. I can run around.
Any questions
Right.
that people didn't ask during the talk?
For the origami robot, what do you imagine to use it for? Like, what application do you have for it?
That's a great question. So, one of the things that I want to use it for, or I want my my lab to begin demonstrating, is for as a trunk-like arm for being able to in a much lighter form factor for grasping and manipulation. So that's something that we're working on now, hoping to come out with that work in the next year or so.
Hi, thank you so much for the really cool talk. I noticed with the Kresling patterns, since you guys printed with TPU, I guess I'm more used to I've made a paper one before from a little class that we did, and I noticed with TPU it seems to not at the folds at the bottom towards the planar areas, it seems to not fully fold all the way. Mm-hmm. I was just wondering if that has been an issue or because it's a different material. I know you guys ran the other tests to show that the models still hold. But like in terms of just like, was it annoying to deal with that, or other things like bending? Like I know we talk about like rotating and compressing, but what about like actually bending in the way that you don't want it to, because it's like, I guess it's a little softer than like paper. I don't know if that made any sense, but yeah.
No, that's a great question. One of the things that we spent a fair bit of time figuring out was what the right ratio of wall thickness to height was, so that we could get the best fold-like behavior rather than the faces just buckling. If you make the walls too thin, you get the buckling. If you make the walls too thick, it doesn't want to fold at all. So that is something that we still run into when we change scale. We kind of have it dialed in now for like, it works, please don't mess with it. But yeah, that is absolutely a challenge about when it does behave like paper and when it doesn't, and the answer is not consistent across all designs.
Awesome. Maybe I'll jump in with a question. So this is super cool, Kris. Something that I'm curious about, sort of as an outsider looking at all of these cool different types of actuators, in particular with the Kresling units, is I'm guessing that it can be more of a feature than a bug, the fact that these are actually flexible structures. So we're talking about it as a 1 degree of freedom, sort of rotate and translate type actuator, but it seems like it actually is possible to sort of rotate one base with respect to the other. So in theory, they would stay parallel, but in practice, they don't necessarily have to. And I'm curious how you think about sort of this non-rigidity allowing you to do other things with them. I saw, I think for one, they had like this little parallel actuator where you had multiple Kreslings, and so you were able to sort of tilt a plane, which you wouldn't be able to do if it was actually rigid. So yeah, how do you think of that sort of playing into the options?
Yeah, thanks. I think that's a really interesting question, and the challenge that my lab is working on now is how do we do it in a reconfigurable and purposeful way versus it naturally occurring as a manufacturing variation. So if we were, for example, to be able to selectively change one of the stiffnesses of one of these hinges so that it does preferentially want to cant to one side as well as rotate and collapse, we would love to be able to do that, and we just haven't quite figured out how to do that with a multi-unit system and like multiple actuation inputs per unit.
I think that's super cool. All right. Any other questions?
So my friend and I in Ghana, we work on designing / testing 3D printed support devices for different people who have like amputations or like splints or things like that would normally be really expensive because prosthetics are really expensive and other medical devices are really expensive. And one of the issues that like we're still kind of figuring out and working on is the point of connection to somebody's body. And it caught my attention when you were talking about how like when you're putting the sensors on somebody's body and stuff and how them wearing it can shift, all that different stuff. And I was wondering like what's been your process and kind of like working through how to get almost like a consistent result or consistent reading.
Yeah, that's a great question about how to get a consistent orientation and consistent sensor alignment. And I struggle with this as an engineer as versus like sort of philosophically, because ideally our approach would be it doesn't matter. You can just put it on however you put it on and it works, which is I think the only way that we're going to get people to have a high acceptance of these sorts of technologies. Like if I have to put on my shoe and it has to be perfectly aligned and I need a little test jig and like I got to tie it the right way, I'm going to be like, that's it. flip-flops today. And so for right now, the answer is, yeah, we're extremely constraining it. We're making sure we have a little handprint that everyone puts their hand in. We make sure that the sensors are exactly this distance away from their elbow joint, and we mark that at the beginning of the test. But that's not acceptable long term. And I'll admit I don't know exactly how we get from here to there.
I was actually just sort of going from that. If your sensor was so cheap that you could, and you had sensors everywhere around, then presumably a hand action could tell you where the bicep and the tricep is. Like, I could just wear the sensor incorrectly and use some sort of data-driven approach to do that, or is that not?
Yeah,
not even in the long term a sufficient way to.
I'm not sure because I'm not sure. I don't know of any good sources, and I don't know of any good sources that say like person-to-person variation for these, like this acceptability of the changes in how I would stand if I did this versus the changes in you would do the same thing, like for that amount of data versus something like a challenge where it's like, okay, pick up this plate and wash the dish. It seems like it's a much higher dimension challenge in some ways, and I don't know. Yeah, I don't know quite how to address it. Yeah.
Sorry, I guess this is like mildly related, but the only type of like, I guess, wearable sensors that I can think of that currently exist right now are like the Garmin sensor, like, like the running sensors, or like the Apple Watch where they're like measuring your steps and your heartbeat and stuff like that. So I guess what is like the difference or like the increased like challenges between that, which, people are using now compared to like the medical applications, and like what are like the problems that need to be solved to like scale it up in a similar way?
Yeah. So I think wearable sensors work really, really well or well enough for our purposes generally. If you talk to like rehabilitation researchers and say, you want to do kinematic studies of the knee joint or the shoulder joint, and I'm going to use IMUs, they will laugh at you. They will laugh at you, and then they will be sad about the amount of money that they have to spend on mocap. So I think that for a lot of like general health stuff, wearable sensors in rigid platforms work good enough. And the challenge is like in places where we need to, in situations where we need to get information that is not easily linked to a rigid platform is where I think the existing challenges are. So, force, great, we can kind of do that already, but skin stretch. And how to not constrain that. That's a very different problem that's like more challenging to measure with an IMU.
Awesome. Great.
Thank you.
Yeah.